Hi, I'm Zor. Welcome to Unizor Education. This lecture would be the last one in series about quadrangles. We will talk about trapezoids. We talked about parallelograms, rhombuses, rectangles, squares. Now it's trapezoid's turn. Well, first of all, where is exactly trapezoid in the whole scheme of things of all the quadrangles? Now, if you remember, I was talking in the previous lecture, I was talking about quadrangle being basically parallelograms which are in turn broken into rhombuses and rectangles, and then square inherits both properties of rhombus, which is parallelogram with all equal sides, and rectangles, which is a parallelogram with all equal angles. Now, where is in this scheme of things trapezoid? Well, basically trapezoid is here. It's not a parallelogram. In a parallelogram, all four sides are parallel to each other. In trapezoid, two sides are parallel and other sides are not parallel. Well, actually, there is some discrepancy as far as terminology is concerned. Sometimes people might say, okay, trapezoid is a quadrangle with two parallel sides, and doesn't really matter what kind of relationship other two sides have, parallel or non-parallel, which makes parallelogram is kind of a trapezoid with two other sides parallel as well. On the other hand, we can say that, okay, trapezoids are actually quadrangles which with only two sides, opposite sides, parallel to each other, and other two sides are not parallel. It doesn't really matter. I mean, it's just terminology. And speaking about terminology, there is another trick here. You know that Europeans and Americans sometimes are calling the same thing with different names and different things with the same name. Like the football, for instance. I mean, in America it's one type of a sport, and in Europe it's completely different. Or let's say in a decimal number, what's the separator? Integers, integer part from the fractional part. In America it's dot, and in Europe it's comma. So anyway, unfortunately we have the same kind of a problem with trapezoids. Trapezoid is something which I just explained, a quadrangle with two parallel sides, and two other sides are not parallel, something like this. And there are certain quadrangles with all four sides not parallel to each other. Well, it's not the right kind of a picture, but something like this. Okay. All four sides are not parallel to each other. Now, this might be called trapezia, or trapezium. Trapezium. Well, unfortunately, in Europe, terms are reversed. This is called trapezium, and this is called trapezoid. Well, I'll stick to American side, just because I have to stick to something. So let's consider I'm calling the trapezoid this type of a figure. These two sides are parallel. Okay. That's some kind of an introduction into trapezoids. And now, as with everything else, we will talk about different theorems, different properties of trapezoids. So I do have my piece of paper where I put all these theorems one after another. Now, what's different, by the way, in explaining the trapezoid, let's say, from something like a rectangle. In case of rectangle, we have inherited certain properties which we have proven before for parallelograms, because rectangle is kind of a parallelogram. Same thing with rhombus. With parallelogram, we didn't have anything before it. So everything for parallelogram, we were just proving one by one all the theorems, and all the properties were unique for parallelogram. We didn't really go to any prior theorems to refer to. Now, same thing with trapezoid. Since trapezoid doesn't have any predecessors, it goes straight from quadrangle. So all the theorems are basically will be proven anew, and they're really very easy and very short ones. So anyway, number one, bases of trapezoid are not congruent to each other. Well, this is actually following from the definition almost directly. Now, these two sides, which are opposite to each other and parallel by definition of trapezoid, are called bases. This is base and this is base. If you want, this is upper base and this is lower base. And these sides are called legs. If you wish, left and right leg or whatever. Now, why are bases, why they are not congruent to each other? Well, you remember, you have to remember the theorem about parallelograms, that if two sides, opposite sides of a quadrangle, parallel to each other and congruent, then this is a parallelogram, which means all other sides also should be parallel to each other. But we have actually defined our trapezoid as a quadrangle with only two opposite sides parallel to each other and two other not parallel. That's why these bases cannot be the same. One is smaller, one is bigger. And obviously they can be this way or this way. This is also trapezoid, or this way. So whatever way we can put all these sides as a non-parallel, in a non-parallel position is good enough. So these are all trapezoids. And that's why the theorem number one was that the bases are not congruent, and this is obvious from the properties of parallelogram, as I was just saying. Theorem number two, okay, it refers to isosceles trapezoids. Now, isosceles trapezoid is the one with legs congruent to each other. So it might be this position, or it might be this position, as long as these are congruent to each other. So either they're both going outside or both goes inside relative to the bottom. That makes top smaller and bottom bigger, or top bigger and bottom smaller. I'm talking about bases. Obviously they cannot go this way, because that would make it a parallelogram, right? So let's assume we will draw the picture like this. It's just more convenient and more habitual to me. So isosceles trapezoid, ABCD. And isosceles means BC is parallel to AD, and AB is congruent to CD. That's what isosceles means. So, angles formed by base AD with two legs are congruent to each other. That's what's necessary to prove. Same thing with these two angles, which this base forms with two legs. Okay, how can we prove it? Let's drop two perpendiculars. Now these two perpendiculars are congruent to each other because we have already proven that if you have two parallel lines, then the distance is basically constant, and this distance is measured by the length of the perpendicular. Okay, so these two guys are both perpendicular to the same AD, so they are parallel, and since it's distance between two parallel lines, they're congruent as well. So they are parallel and congruent, which means that, I mean, just incidentally, that this is a rectangle, if it's important. So BC and M is a rectangle. All right, now, what do we know about these two triangles? Well, we have two congruent hypotenuses, because this is isosceles trapezoid, right? Now, obviously, these are right triangles because CN and BM are both perpendiculars. And also, the catetus BM is congruent to catetus CN of this triangle. So these two triangles are congruent to each other, which means these angles are also congruent to each other. That's it. Now, how to prove the congruence of these two angles? Well, just looking at the picture, you see that since these angles are right angles plus congruent acute angles of these two triangles, that makes these angles ABC and BCD also congruent to each other. So again, ABM is the acute angle which is congruent to MCD, and then to these two congruent acute angles we have added 90 degrees from this rectangle. So that makes it also congruent to the sum of these two angles. Okay, so that's done. Theorem number 3, in isosceles triangles, angles are supplementary to each other. Well, we can do it many different ways. First of all, we know that in this triangle, two acute angles are always sum up to 90 degrees, right? So if we add another 90, we get 180, and that's what makes these two angles supplementary. On the other hand, there is I would say, a little bit more elegant, if you wish, solution, proof actually to this theorem, as follows. Now, we know, and again, we have addressed this before, that every convex quadrangle has sum of its angles equal to 360 degrees. Now, since these two angles are congruent, and these two angles are congruent, so the sum of these four angles is 360, but it can be basically divided into two pairs. This plus this, and it's equal to this plus this. Since these are congruent and these are congruent, then these two sums are supposed to be the same, which means each one of them is equal to 180. Sum of this, same as sum of these two angles. So that's a little bit more elegant, I would say, but it doesn't really matter how you prove it. Anyway, so the angles which leg makes with two bases are supplementary to each other. Okay, number 4. Median of a trapezoid is parallel to its bases and equal to half the sum. Okay, I have to draw another one. So, first of all, we are talking about trapezoid, not necessarily isosceles. Now, median or mid-segment or midline is a segment which connects two midpoints of two legs. Now, the theorem states that this segment, MN, is parallel to both bases, and its length is equal to half the sum of these two bases. So if you add this to this and divide by 2, you get this one, which looks actually kind of, you know, it looks like it really is half of the sum, because it's in between. This is smaller, this is bigger, and this is in between. So that's what we want to prove. Now, how to prove it? That's actually easy. All we need is to think about one particular extra line, call it X, and let's consider these two triangles, BCN and NXD. Now, these angles are vertical. Now, these angles are alternate interior angles with BC and AD parallel and CD as a transversal, which means they're also equal, congruent to each other. And this segment CN is equal to ND because N is a midpoint. So we have angle side angle, which means that this is equal to this, and this equals to this, right? From the congruence of these two triangles. All other elements are congruent as well. Now what do we have? Let's consider ABX triangle. Now, MN is a mid-segment in this triangle as well, because this point is middle of this segment by condition of the theorem, and point N also divides BX into equal parts. So N is midpoint of BX. Now we know about the triangles that the mid-segment is parallel to the base and is equal in length half of the base. Now, what is the base? But the base is actually sum of two bases of our original trapezoid, because it has AD plus another segment which is exactly congruent to BC, to our upper base. So the base of this triangle, ABX, is actually sum of bases of this trapezoid. So MN is equal to half of the base of this big triangle of AX, which is sum of the bases. That's why MN is parallel and equal to half of the sum of two bases. And the proof. Okay, what else do we have? Line connecting midpoints of two bases of isosceles trapezoid is its axis of symmetry. So these two are congruent and these two are congruent. So X and Y are midpoints of AD and BC. Now, how can we prove that points A and D, as well as B and C, are symmetrical relative to this line? Okay, here's how I propose to do it. Again, all the problems actually in geometry are going exactly the same way. You have to find some triangles which are equal to each other, congruent to each other, whatever. So I find I find these two new segments to be convenient in this particular case for the proof. Now let's consider triangle ABX and XCD. Well, obviously I would like to prove their congruence. How? Well, since this is a isosceles trapezoid, then this is equal to this. That's basically the definition of isosceles trapezoid. Now, we have just proven before that two angles at the base of isosceles trapezoid are congruent, are congruent. It makes these two triangles, ABX and XCD, congruent by side, angle, and side. Now, what's the importance of this fact? Importance is that these two segments are congruent to each other as well, which makes XBC an isosceles triangle. Now, in the isosceles triangle, as we know, median, and XY is a median because it divides the BC into halves, is also an altitude and bisector of the angle and segment bisector, etc. So it has all these properties. But what we are interested in is perpendicularity. It's since it's altitude, it's perpendicular. XY is perpendicular to BC, and that's basically it. Because if this is perpendicular, and B and C are on the same lengths from the axis lying on the perpendicular to this axis, that actually is a definition of symmetry. Now, same thing here. So XY, since it's perpendicular to BC, it's also perpendicular to AD as well, because these are parallel. And these two segments are congruent to each other, and that's what makes A and G symmetrical relative to the line XY. Well, that's basically it. Since these points are symmetrical to these, then the whole figure is basically symmetrical. Okay, so as I was saying, this is the last theoretical lecture about quadrangles. There might be some problems, obviously, and don't forget that every topic actually has an exam associated with it. So if you go to unizor.com and you sign in as a student, you will be enrolled by a supervisor or your parent into some kind of a program where you will have to go through theoretical material like this and exams, and your score will be visible to your parent or supervisor, and then they can actually decide whether to pass you or fail. Well, if you fail, don't despair, just listen to the lectures again and try exam again. It's a relatively small number of problems which you have to solve. It's a multiple choice, so just try it and you'll do best, I'm sure. Okay, thanks very much for today. That's it. Thank you. Good luck.